Tesla's $10,595. Model 2 shatters the myth that EVs are only for the rich. It proves smart, sustainable transport can be affordable. Elon Musk's vision of electric mobility for all is finally real. The 2026 Tesla Model 2 marks the ultimate realization of Elon Musk's long-game strategy, the secret Tesla Motors master plan. What began with the premium roadster and evolved through the mass-market Model 3 and Y now culminates in a truly affordable, high-volume vehicle. The goal has never been just to sell cars, but to drive the world's transition to sustainable energy. The Model 2 is the lever designed to move the entire global automotive market away from hydrocarbon-based vehicles by offering a compelling alternative on price, performance, and long-term value. With a targeted price significantly under the average new car cost, the Model 2 is intended to be the death knell for the entry-level internal combustion engine (ICE) vehicle. The Model 2's financial viability relies entirely on radical cost compression, which is achieved through integrated design and process innovation, moving far beyond incremental improvements. The $2,000 savings in material and logistics costs achieved by consolidating parts through gigacasting is just the starting point. This efficiency is amplified by the sheer reduction in manufacturing footprint and complexity. By employing single-piece castings for the front, rear, and structural battery segments, Tesla has removed thousands of complex welding, stamping, and bonding steps. This simplification not only reduces material usage, but also allows for a highly automated assembly line, cutting down on quality control bottlenecks and saving roughly $1,500 in direct labor costs per vehicle. This level of vertical integration and manufacturing mastery creates a profound multi-layered cost advantage that traditional automakers relying on legacy assembly plants and supplier networks simply cannot replicate quickly. The unboxed modular assembly process is arguably the most significant disruption since Henry Ford's original assembly line. Instead of a single linear line where workers slowly add parts to a constantly moving shell, the Model 2's core modules, the front casting, the rear casting, the structural battery, and other sub-assemblies like the doors and seats, are built simultaneously and independently in parallel assembly cells. Only in the final stages are these large, pre-integrated components brought together and snapped into a single car, dramatically reducing the overall build time. This allows the various stages of the factory to operate at their own optimized speeds without being limited by the slowest common denominator of a single line. The targeted chassis production time of 4.7 seconds per car is a testament to this architectural shift. This modularity allows for unprecedented scaling and flexibility. Should there be a supply issue with a particular module, the other parallel lines can continue production, minimizing the complete factory shutdown common in traditional plants. The AI control system, leveraging Starlink's low-latency communication for real-time sensor data, acts as the central nervous system, ensuring every robot is operating optimally and catching errors before the component is even integrated. This proactive quality control, built into the process rather than relying on a final inspection, is another key to unlocking mass production quality. The planned production volume of several million units annually across multiple gigafactories, including the flagship Giga Texas and new facilities like Giga Mexico, hinges entirely on the successful deployment of this unboxed assembly model. The choice of the lithium iron phosphate (LFP) battery is the economic linchpin of the Model 2. While LFP cells have a slightly lower energy density compared to the nickel-based NMC-NCA cells used in long-range models, their advantages align perfectly with a cost-focused, durable vehicle. Their affordability stems from using widely available iron and phosphate, sidestepping the volatile costs and ethical concerns associated with cobalt and high nickel content. This cost differential is further exaggerated by the battery's design as a structural component. By shedding the weight of the traditional pack enclosure, the Model 2 compensates for LFP's lower energy density, allowing its 53 kilowatt-hour pack to achieve an estimated range of up to 307 miles, more than sufficient for the vast majority of daily driving and making it competitive with vehicles in higher price brackets. Furthermore, the integrated structural pack contributes to the vehicle's high torsional rigidity, enhancing crash safety and handling, proving that affordability does not necessitate a compromise on structural integrity. One of the Model 2's most overlooked yet transformative innovations is the radical simplification of the vehicle's wiring harness. Traditional premium vehicles can contain up to 4 kilometers of complex wiring, a costly, heavy, and labor-intensive component requiring human assembly. Tesla's previous Model 3 reduced this dramatically, but the Model 2 introduces a design philosophy aiming for a near single wiring harness architecture, a reduction of over 70% in wiring length compared to the Model 3. This is achieved by strategically placing localized, intelligent control nodes throughout the vehicle. Instead of running a dedicated wire from the central computer to every component, every speaker, window motor, and sensor, Tesla uses a robust data network, essentially an Ethernet-based backbone, that communicates with these local nodes. These nodes then directly manage the components in their immediate vicinity. e.g., one node controls all 4 door functions. This innovation not only shaves off a significant amount of the 17 to 30 kilograms of copper typically found in an EV's wiring system, leading to substantial material cost savings and reduced vehicle mass, but also massively simplifies the assembly process, making it far more amenable to robotics and automation. The reduction in copper demand per vehicle also serves a critical long-term strategic goal: mitigating the future impact of rising global copper prices driven by the electrification of the transport and energy sectors. This technological leap addresses a bottleneck that has plagued automotive manufacturing for decades, offering a genuine, proprietary, and difficult-to-imitate manufacturing advantage. The most transformative aspect of the Model 2 is not its hardware, but the monetization strategy enabled by its software. Full Self-Driving version 14, FSD 14. For the mass market, the promise of the robo-taxi service fundamentally changes the relationship between the consumer and their vehicle. Traditionally, a car is a rapidly depreciating liability. The Model 2, however, is being positioned as a profitable asset. The robust, low-maintenance nature of the Model 2, derived from its simple gigacast body, minimal wiring, and long-cycle LFP battery, is an ideal foundation for a commercial vehicle. The long cycle life of the LFP battery, in particular, ensures that the pack can endure the high-frequency charge/discharge cycles inherent in continuous taxi operation. The projected earnings of over $35,000 per year for owners who allow their car to operate for 6 to 8 hours daily are not based on fantasy, but on projected revenue generation in dense urban environments. This passive income stream has a profound macroeconomic implication. It makes the total cost of owning a technologically advanced electric vehicle potentially negative. The continuous improvement of FSD V14 is directly powered by Tesla's Dojo supercomputer. Dojo is not a general-purpose supercomputer. It is a custom-designed, purpose-built machine for training the massive visual neural networks required for end-to-end autonomous driving. Its specialized D1 chips and scalable architecture allow it to ingest petabytes of real-world driving data, the millions of video clips collected by the global fleet at an unprecedented speed. Dojo's goal is to rapidly iterate the FSD software, quickly identifying and training for edge cases, rare, complex driving scenarios that are crucial for achieving true Level 4/Level 5 autonomy. The massive computational advantage provided by Dojo ensures that the Model 2's autonomous capability, the core driver of the robotaxi revenue stream, will constantly improve, maintaining a vast lead over competitors who rely on less integrated, less efficient training pipelines. The Model 2 is entering a global market currently experiencing intense competition, particularly from aggressive, low-cost Chinese EV manufacturers. Companies like BYD have already demonstrated the ability to produce high-quality, LFP-based EVs at low prices. The Model 2, therefore, must do more than just match their price point. It must offer superior technology, manufacturing efficiency, and the unique value proposition of the FSD ecosystem. Tesla's use of integrated hardware and software, from the custom neural net chips, Dojo, to the FSD software and the revolutionary body architecture, gives it a systemic advantage over rivals relying on supplier components and traditional manufacturing. The vehicle represents Tesla's defense against, and eventual offensive against, the entire global affordable car market. However, the innovation in manufacturing poses a significant challenge regarding vehicle repairability. a factor that directly impacts insurance costs and the total cost of ownership, TCO, while gigacasting significantly reduces manufacturing costs and improves structural rigidity. Critics argue that the consolidation of the vehicle structure into a few massive components can lead to vehicles being totaled more easily after moderate collisions. If a major cast component is damaged, the repair procedure involves replacing the entire large casting, which is a complex and expensive procedure compared to replacing a dozen small stamped metal parts. Recent research suggests that while repair costs for minor damage may be competitive, the threshold for a total loss is indeed lower. Tesla is proactively addressing this by designing the castings with strategically located sacrificial zones and clear, documented repair guidelines for the attachment points. However, the long-term TCO benefits of the Model 2 will heavily depend on how well the insurance and repair industries adapt to this new paradigm of high-volume structural casting. The ultimate impact of the Model 2 extends to urban planning and energy infrastructure. If millions of affordable, autonomous EVs are deployed, it will dramatically shift the need for personally owned stationary vehicles. Widespread deployment of robo-taxis could reduce traffic congestion and free up vast tracts of urban space currently dedicated to parking. Furthermore, the Model 2's mass market demand creates enormous pressure on the global battery supply chain, accelerating the move toward abundant materials like iron and phosphate and driving down costs for all energy storage applications, from cars to home power walls. The Model 2 is not just a car. It is a critical component in Tesla's larger vision to become a distributed global energy and AI company. Elon Musk's ambition is to reach production volumes of 20 million vehicles per year by 2030, a goal achievable only through the hyper-efficient capital-light manufacturing methods pioneered with the Model 2. This monumental scale necessitates a complete rethinking of global supply chains, from raw material extraction to final assembly. The Model 2 is designed to be a universal product, adaptable to global regulations and consumer tastes with minimal retooling. Its projected manufacturing hub in Mexico is intended to serve North and South America, while gigafactories in Europe and Asia will handle their respective regional demands. This geographically distributed, yet technologically unified, production strategy ensures that the Model 2 can conquer the global market simultaneously, securing Tesla's place not just as an automaker, but as the dominant force in the coming era of sustainable and autonomous personal transportation. The combination of sustainable transport and energy-positive ownership is intended to complete the transition to a sustainable global energy matrix. Thank you for watching, and don't forget to hit the subscribe button.